Welcome, everyone. This is our second workshop of the Thursday series, NLP for All. My name is May Krishnaswamy. I'm a grad student at the Department of Linguistics. Hello to everyone in the room. Sorry about that. And today, just to start us off, I'd like us to start with a simple discussion on what got us into natural language processing as a field. And in order to assess this, let's start with a simple question. And the simple question here is, if you had a machine that did not know human language at all, what would you do in order to get it to understand you? What would be some very preliminary, simple things that you can do to get started with talking to a machine? And you can answer through the chat, or you can raise your hand, that also works, or you can unmute yourself and talk if you're in the meet. Absolutely right. Yes, we start with some kind of character encoding. If we are using the medium of text to talk to our system, we want to make sure that all the characters that we use translate into zeros and ones. So that would be the first thing. Okay, so now our system has an understanding of what A, B, C, D mean. What's next? Would that be sufficient for me to tell my computer to open a file or ask it how the weather is today? Kyung, you're a linguist. Do you have thoughts?
So for text, we should know what words.
Right. So the next step is we have our characters and we want to build from our characters to words. So we want our system to be able to differentiate between different chunks of characters. So we want it to understand that a space means one word ended and another word began. We wanted to know that a full stop means that an entire sentence has ended. So we try to get our system to understand what words are, right? So now we have words, we got to the character level. What would be the next step, logical step in trying to understand how to do this? Right, yes, speech to text first, absolutely. And yes, Mike B, that's correct. The next step is we want our words to have a meaningful relationship with each other. Words do have meaningful relationships with each other in natural language. We want our system to know what this relationship is. So if there is a sentence, there is some kind of a relationship between word A and word B and word C. And if our system does not know the meaning, the relationships between these words, then we're going to be lacking in explaining what we want to our system. So we want our system to be able to get some sense of the syntax of our language. Let's add a few more layers. Okay, so our system has some blind understanding of word A and what word A next to word B means. But do all words in natural language, we like to classify words into different categories. So not only do we have syntax, but we also have semantic categories. There is a meaningful difference between a ball and running, or cat and meow, and eating versus healthy, right? So we have adjectives, we have adverbs, we have nouns, and we want to be able to ensure that our system is able to categorize or bin our words into different categories, right? So in order to achieve all of these tasks, natural language processing as a field has been working on a lot of these interesting tasks. And even though as of today we do have amazing large language models that can automatically do this, you can brute force your way to explaining anything, any piece of language to a model and get the kind of output that you want. While we are on the journey to understand how AI processes things and how we make a large language model understand this, some of the small building blocks steps to getting there is essentially what we'll be targeting in this particular workshop. So natural language processing part of the workshop's title is just this: how do we make sure that our system knows what components of a human language are what? The second part would be the for all part. And the hope is that irrespective of what field you come from, I would work with an assumption that if you are doing any kind of research, or you're playing any part in an education atmosphere, there would be a lot of text, a lot of data, a lot of things that all of you will be working with. And NLP for all part comes in basically trying to communicate some of these essential natural language processing tasks, and for us together to see if there are applications, not just in the niche field of, say, linguistics, but moving broader to whatever fields that all of you work in, right? And as always, since we are working with data, if your data happens to have language, it might be worth it to see if there are some specialized tools that can help you get to where you need to get. Right. So with that, let's get started. The first thing I'd like you to do is get to our GitHub repository. So let me add it to chat for everyone who is joining us remotely. And for those of you who are joining us in the room, the URL is github.com/ua-datalab/NLP-speech. The link is also available in the calendar event that all of you may have worked with to get here. Oh, give me one. This is an unusually tall chair. All right, so this would be where we will be housing all of the workshop materials going forward. So every time, if you're going to be, and I hope that all of you will be joining us for future sessions, you could the table right at the bottom will also contain links to the specific materials. The hope is that each workshop will lead you to one Google Colab notebook, and we will try our best to stick to running things on the browser and keeping the tech aspect of our workshop as low resource as possible. So for today's workshop, I invite you to click on the link to notebook right here, which hopefully will take you to a part of the repository with a little button on top which says Open in Colab. Just for anyone who is getting started with Colab, if all of you are completely caught up on this, awesome, right? So if you click on Google Colab, this should open a version of the code on your own Google Colab account. And I invite you to engage with the notebook, make changes, take notes, save your own version of the notebook. And if any of the code here sparks an interesting project, I hope that you'll find something to add. All right. So first, let's start with some definitions as we go forward. First, natural language processing, broadly speaking, is a machine learning technology with the purpose to automate some aspects of interpretation, manipulation, and comprehension of human language by computers, right?
Hey,
And
Meg, can you share your screen?
Sure, good point. Let me do that. Can you see my screen?
Yes, all good.
Great, thanks. All right, so currently one of the main applications for all the NLP tools and technology has been development of AI. It is by no means the only task or the only challenge. At its heart, we're operating with an assumption that whenever most cases where a machine needs to work with natural language, if we have the ability to make viable predictions and use statistics, that should be enough. Now, as many of you, if you've worked with ChatGPT at all, if you've tried your hand at working with different AI tools, you know that sometimes this assumption fails. But for the purposes of our workshop and for NLP as a field, we are operating with the assumption that sometimes predictions are all we need, right? Next, as far as the current state-of-the-art system is concerned, we are working with big models that are using billions of lines of human-generated text. We fed it everything that humans have ever possibly said on the internet, ever written about, ever said as part of movie dialogues. We gave all of it to these extremely big, complicated, sophisticated machines, and they have now developed the ability to predict what you're going to say if they see it, if you give it a prompt, right? It's amazing. And the scale at which all of this has been working combines knowledge of what a word is, what phrases are, how do we provide a mathematical representation of all the language at different levels. And we're trying to teach it to mimic human responses, right? So that's where if you've heard the phrase stochastic parrot, that's kind of where it comes in. Right now, some of the NLP applications we've talked about. If you were there for the previous session, we talked about sentiment analysis. We talked about chatbots a little bit. There's machine translation, text summarization, spam detection. There's all kinds of information extraction, and the broader elements of this kind of training is also being used for things like drug discovery, which have almost nothing to do with natural language, right? Now, whenever we talk about these bigger models and how they work, the one theme of this is that if you take a lot of data, you take a complete maximalist approach, you feed it everything, you're going to get an amazing pre-trained model that's going to have every aspect of natural language, and it's going to use all of that information to do a task. And there is a certain amount of distance between us as the users of this technology and the model itself that's shrouded in that uses all kinds of sophisticated pipelines, that's using its own interesting things for training. And one of the ways in which we can better gap this distance is to see how we got from all kinds of text, all kinds of data, all kinds of words to a sophisticated model that understands, that can understand and to an extent understand and mimic human language, right? So here comes a question. What are the available tools for us to process natural language? One of the common tools, NLP tools that's used these days is SpaCy. Right, it's free, it's open source, and it is a series of libraries for advanced natural language processing, right? And something that makes SpaCy stand out is that it's written with keeping in mind memory constraints and production quality. So not only besides the aspect of pre-training or working with transformers, SpaCy might be a simple, easy, first step initial tool that all of you can use in order to get started with some kind of an NLP task, right? Next, if there are a lot of SpaCy resources, and I will cover what I can in an hour, but if you are interested, SpaCy's website has lots of tutorials and many ways in which you can engage with the software itself. And to keep the conversation going, one of the things that SpaCy also offers is an NLP pipeline, right? Now, we talked, we talk a little bit about feeding a pipeline or opening up a pipeline to work with a language model. And what we can do today is kind of look at some of the components of the pipeline itself and what it means to turn a document into a SpaCy data set. Right. So some of the main things that we'll be covering today is tokenization, stop word, and special character removal. We'll be talking very briefly about lemmatization and see how we can use all of these for some specific tasks, such as similarity calculations and name entity recognitions. And I will touch on all of this. So the first question is, how would SpaCy work? What is it essentially doing? The main thing that SpaCy does for us is it takes a text that you provide, which in SpaCy language, I believe is called it would just be called a text. It passes it through a natural language processing pipeline, and it's dividing up your entire text into different words based on a language model that you choose. It's telling you what, it's adding different kinds of tags to the words that you have provided. Again, something that may be very language specific. It's parsing, so that is, it's dividing up your sentences. It's dividing up your sentences into phrases and so on. And it does there are some other interesting things that it does. It looks for entities that that sound like names. And so if you're looking for technical terms, you're looking for the names of specific people, there's an NER processing component that SpaCy can use. Finally, it will output a document which basically ensures that every chunk inside your text now has a whole bunch of very NLP relevant tags that you can then use for further downstream tasks. So first, in order to set up and load SpaCy, we're going to run the first code chunk, which simply imports SpaCy, right? And the second thing that it does is it downloads for us a language model. So today we're just going to work on some very simple examples in English. SpaCy has a lot of other language examples. And if you are a non-English speaker, the best thing that you can do after this workshop is to see if SpaCy's language model for your language does a good job or not. Right. So if you, at the end of running the first and the second code chunks, you should have a little document that gets printed for you at the end of it. It might take a couple of minutes because the language model is downloading, but you should see a little list that gets printed for you at the bottom of the second code chunk. And what we've done here, I gave the SpaCy pipeline a bunch of sentences. I chose these from Wikipedia's entry on horror. And I told it to pre-process and print for me the first 5 words that it's seeing, the first 5 text elements that it's seeing. And that's what I got. All right. Now, let's look at some terminology for what are the parts of a piece of text or a document that SpaCy is generating for us. First is, if you have the entirety of your SpaCy output is referred to as a document, right? It can have 1 sentence, it could have 10 sentences, it could have 1,000,000 sentences, just depends on what you gave it. Next, we have a span. A span is just a portion of a sentence that is user specified. So it could be the first 5 words, it could be the last 5 words. Anything that's a series of words that are in a sequential order would be a span. Then a token here is just a word, could be at the word level or a character level. So whatever level you want SpaCy to work at, your token would just be one example of that level, right? Then we have our sentence, very similar to the English definition. Then we have 2 other new definitions, which are vocab and lexeme. So a vocab is just a cluster of data entries. So it's every word that has a meaning that SpaCy recognizes as a word. And a lexeme is every specific entry inside the vocab, right? So now with this, there's a little diagram that I got from the SpaCy website to sort of illustrate this. Next, let's see what it means to process a document with our language pipeline. So in this code chunk, there are a whole bunch of sentences. Now SpaCy doesn't know these are sentences. I just threw a bunch of characters at it. And what I'd like you to do is when you run this code chunk, right, see what it does. So when you run the code chunk, you'll notice that the print statement is asking SpaCy to look at entry number 5 in its document, and entry number 5 corresponds to the word origin. Entry number 6 and corresponds to origins since Python starts count at 0. Right. And next, if we want to work on this, and let's try looking at the first 10 tokens in our document. So in the next code chunk, all it does is just pull up the first 10 tokens inside our document, and you can change 10 to any number that you'd like. So if you're just looking to extract a bunch of tokens, you just want to see what are the different word level entries. This would be how you do it. Next, to make things more NLP focused, we might want to look at spans and sentences. And for that, we would use the doc.sense. That's the name of the specific code that you might want to run. So doc is simply calling your document, and sends is just looking at your document at the sentence level, right? So I just wrote a very simple for loop that simply prints a bunch of sentences in a given document, right? So you'll see that that SpaCy has managed to extract a sentence starting from a capitalized letter to a full stop, which is one of the ways in which SpaCy recognizes sentences in English, right? Next, if you want to go into the vocabulary level, you want to see what sits inside the vocab. You'll notice that if you try to access vocabularies with .vocab or with strings, you'll notice that every entry has a hash, which is a unique number assigned to every lexeme inside the vocabulary. And if you if you call strings, then the actual human readable word associated with the entry will get printed, right? Now, besides simply blindly accessing sentences, accessing words, we can also look at what is at the different types of classifications that SpaCy does for us, right? So the first thing I might want to know is, what if I just want, I don't want any full stops, I don't want any special characters, I just want the only tokens that I am interested in are tokens which pertain to human language. So for that, I could run token.isAlpha. So I just written a very simple for loop that simply goes through your document and pulls up any token that has alphanumeric characters, right? So all of our full stops, all of our anything that's your quotation marks, question marks, all of them will immediately disappear. 1 second. Keith, to answer your question, I don't think you'd need to make a copy, because in each case, SpaCy is calling the main document, and it should be able to give you your output without affecting anything that's above the pipeline. So if it would be worth it to make a copy if you want to save things, but I think you could work without making one. All right. Next is let's look at the linguistic features that we can find when we have a set of tokens, right? So first would be just the lemma level. Now, as you know, there are different words. If a word has a pluralization marker, or it doesn't have a pluralization marker, ultimately the meaning for both of the words could be the same, right? So at the lemma level, we stop, it gives me an entry for every word, irrespective of what, of whether it's singular or plural, or if it's a verb, if it's in different tenses. So it accesses the meaning level of a given token. So if in this code chunk, I'm just simply calling a bunch of different words. Now, you'll notice that for the entry origins, the lemma level is just origin. So if you had a document and you were interested in basically accessing every entry pertaining to running, for example, you want to make sure that the words running, ran, run are all classified as the same thing. And for that, using the lemma level would be useful. Next, SpaCy also assigns parts of speech tag, which are extremely useful and a very important part of any pipeline that gets used by language models. And the way to access the tags is token dot, it's the dot POS, right? That would be the chunk that you ran. Now I just created a little print statement that gives you the POS tag as well as the POS label for every entry in a given set of words. Now, if you look at the output here, you'll notice that the word "the" is assigned the label determiner, horror is assigned the label noun, and so on and so forth. And if you're wondering, I wonder why this is interesting or why this is important, remember, like in a lot of languages such as English, a lot of our meaning lives in very specific words. Most of the meaning, most of the important content of your text is more likely to live in the nouns and the verbs and the adjectives than it is to live in the determiners and some of the other stop words. So when we are processing our text, and in this case, I'm just processing 10 words, but what if you had 8 billion words? An intelligent way to ensure to minimize your overhead and make sure that you're targeting your models in an accurate way would be to use the pause tags to only save the things that are relevant to your search and exclude other pause tags that are simply not relevant. Right. Just give me a second. Let me just check if there are any. I'll get back to your question, Keith. Just give me a minute. Right. So next, as Kyung pointed out, we and others pointed out, when we talk about processing language using a machine, we want to make sure that syntactic dependency, that is the relationship between different words in a sentence, is something that can be shared and understood by the machine. And this is where SpaCy's syntactic dependency functions come in. So in order to access them, you use .dep underscore. This would be the way to access basically the different labels and that are associated with the dependencies. So you'll notice that by calling POS underscore and calling DEP underscore, instead of getting like a bunch of numbers, SpaCy is the code written here is printing for me human readable labels, right? So for every part of speech, it tells me that these is a pronoun. It's telling me stories is a noun. And instead of saying these is 81376. So when we use the underscore part of the code, that gives us a human readable output, right? And if you look at the entries for DEP and head, you'll notice that we're getting the different syntactic level information for every word in this given sentence, right? So we've got the label punctuation, we've got conjugation, conjunction. You have labels for in the dependency level, it's telling you what the nouns are and what the verbs are. So here is, I guess, the most important thing that any NLP pipeline can do for you. When we are trying to extract the important aspects of our text or the meaning carrying elements of our document, we can use the syntactic dependency level as well as the parts of speech tag in order to improve it. So now, having looked at all the different labels that SpaCy will assign to a text that you give to it, provided you specify a language and a language model, what can we do with all of this? So one of the simple tasks that you can carry out, for example, could be a named entity recognition task, where it's simply first, if I'm just printing all of my different tokens, token texts, right? Let me, just give me 1 second. Right, let me skip over named entity recognition. I'll come back to this. Something that you can carry out simply would be removing stop words and removing punctuation, right? And so this can happen with a very simple, almost with just a few lines of code, where you have removed a considerable number of your stop words and preserved the words that are relevant to your text. Now, in this specific context, SpaCy has preserved the article as well, just in case it adds some kind, it is meaningful to your search. But we managed to remove a considerable number of stop words, and we end up here with mostly nouns. Now, in case a lot of this is not human readable, as there's a considerable number of abbreviations that get used in the pipeline, something that you can do is always use the .explain code to understand what a particular label means, right? So NNP is noun proper singular, and the label noun simply means noun. And so in case you're using SpaCy and you're not sure what a particular label means, this would be one way to understand. Now, another simple little tool that SpaCy offers is a similarity calculator. And a similarity calculator essentially uses all of the skills that we have seen so far. It's not paying attention to, it may not be paying attention to stop words as much. It's not looking at punctuation. It's trying to look at the different named entity entries in your different text. And it's making an assessment of how similar two given sentences are. Another layer that is operational here is a lot of words, depending on their meaning, might be closer to each other than all other words. And if you look at the simple sentences that I used in this example, I like horror movies and I like scary films. The words movie and the words movies and movie and film have almost have near identical meanings, and the words scary and horror tend to have a meaning that is very similar to each other. So based on the meaning of the word, a similarity calculator could be a simple one-shot, couple of seconds way for you to assess if two texts are similar to each other or not, right? Now, there's a little task here that if we could get back to it if there's more time, but essentially if you'd like to assess if a couple of sentences are similar to each other or not, this would be your scaffold code. Right. Finally, I mean, one of the other important things here is vector representations. Now, if you have a background in AI ML, or if you're working on NLP but with transformers, you'd know that one of the ways in which language is represented for a machine is with vectors. It's the mathematical representation of a given entry, and this would be a very broad definition. I'm sure there's more to this. So if you'd like to access the vector representation that SpaCy assigns to different words, this would be the way to do it. So it's just the dot vector that would help you access it. And what is vector representation doing? There's a lot to it, but essentially it's one of the ways in which the distance between different words is understood and mapped. So next, if we want to search instead of searching for just words, if we want to access words at their meaning level, and then make sure that our different words, if they have different parts of speech tag, helping one way in which we could disambiguate our words that may at surface look the same, but may not actually have the same function in a sentence, would be to simply search words by their pos tag. So in the example that I gave, that I've given here, you'll notice that the word love is not, even though it's the same 4 characters, and broadly speaking, the meaning of the word may be the same, the first entry is a noun and the second entry is a verb. So if we were just simply doing a keyword search, our system would tell us that both of these words are exactly the same. However, they are playing different roles in the sentence. And if that is something that would be of interest to you, searching for different entries with their pos tag and by accessing their lemma level would be a nice way to synthesize some of the tools that SpaCy provides. Okay. All right. So having talked about broadly about all the different elements that go into a language processing pipeline, we talked about different types of tags that get assigned. We talked about how words are entered into a vocabulary. We briefly discussed the lemma level for different words. What is something that we could broadly do? Right. So for this, I've set up a very simple task that we can look at today. This is consider a data set that you got from somewhere. And as a person with some very simple NLP skills, you'd like to look at this data set before exhausting all your OpenAI credits or exhausting your HPC hours, right? So if that's something that you'd like to do, we're looking at a simple data set which contains movie reviews and sentiments associated with the movie reviews. And just for illustrative purposes, I've extracted about 1,000 movie reviews from the large data set. And our purpose today would be to see if, without using any big tools, with just a laptop and CPU resources, if we can broadly take a look at this data set to see what's inside it, and try to run some very simple bare-boned NLP tasks on it. Okay, so if you run the first couple of lines of code chunks, it's just a simple look at the data set itself. So if the df.info is just something that would tell you how many entries we have 1,000 entries. We have the column names here, very basic things. And if you look at the head and tail of this data set, you'll notice that the main columns that we are interested in would be the review column and the sentiment column. All right. Now, I have a bunch of movie reviews. I have a bunch of sentiment that a set of human annotators have assigned to it. And as someone who got presented with a data set, I want to understand if this data set is useful for a task that I set, right? Before I assign it to a language model, right? So first, what I would want to do is let's do a little down sample just so that our workshop today runs a little smoother. So I'm taking 500 sentences from the 5,000. So we've got like a random set of a set of 500 sentences. And in order to basically consider looking at the relevant aspects of a review, we might be more interested in like the non-stop words. And so the first thing that I might do with this is to simply remove anything that's a stop word or is a punctuation, right? Just to make things run faster and streamline the task that I have. Right now, once all of this is done, I'll look at our NLP task for today, and I invite you to make changes to it and run your version of this, and not just the example that I'm giving. Right. So the simple NLP task, bare boned, that we want to do today is say, first, we want to find a bunch of horror movies that are reviewed very well and which pertain to a specific genre, right? So let's say if I want to do, I want to look at horror movies, you could be looking at romance movies, action, thriller, whatever kind of movies that you are interested in today. And what we want to do is specifically look at good movies that I can watch with my friends. Now, your task could be to run a bad movie night, and so you could be more interested in looking at movies that have been rated very poorly just for your bad movie night. And in that case, your task might be a little bit different than mine. So because my simple task here is to just check out some positive reviews and see if this data set that I have is something that can give me good movie recommendations. Let me first simply filter out all the movies with negative reviews, because I'm also trying to assess the quality of this data set. Next, what I'm going to do is simply create a simple a phrase matcher that's going to simply look at the word level for different words that I might see in a review about a horror movie. Right now, I've just added a bunch of phrases that sounded interesting to me. There might be more relevant phrases pertaining to horror movies, or if you're in the mood for a action thriller or a romance or a rom-com, your phrase list might look very different from mine, right? So I, at the phrase or the word level, I'm going to search for a bunch of phrases from a given data set, right? So feel free to add to this list or play with it as you like. Next, I'm going to build a little rule for phrase matching. And what the phrase matcher is going to do is, now that SpaCy has processed all the text in my data set and turned it into documents with nice labels and tags, I'm going to utilize all of these labels and tags to essentially match, do a very simple pattern match task where I'm asking, if you see the phrases in my phrase matcher list, bring me all the reviews that contain those phrases, right? So the next two code chunks will very simply run those for you. And at this point, this is just like a very simple task that I ran. The purpose here is I am not sure if this data set, which has thousands of entries, is the right fit for me. I'm using a small randomized sample, running some very simple NLP tools to see if my task and my data set are a good match or not. And what happened at the end of my code run is just a bunch of matches. And for the next couple of minutes, I invite all of you to look at these matches and see if we got a good sense of the data set or not, right? So the first one, it returned me a match about I guess a homicide detective. Right. So the first review is telling me it sounds more like a thriller to me than a horror film. But I would be curious what all of you think. The next one, we've got something involving graves and monks. Sounds definitely more promising. The third case, we got a psychological thriller, and so on and so forth. Right now, there are many ways to build our vocabulary matcher. I added a bunch of interesting words. If you excluded words like thriller, you might get very different settings. And at the end of it, what we get is a small subset of our big data set and a human and machine readable way of looking at the text. Now, at this stage in the workshop, we've only worked at the word level. In the future workshops, we might want to make our search results more interesting with semantic search, where instead of just dealing with keywords, we're looking at relationships between different words to see if our search can be more intelligent. We'll be looking at at a few other tools that contribute to making an NLP task more automated and simpler. So there are also a few other libraries that are very popular for NLP tools. This includes NLTK. There are also other companies that offer pipelines that can help you carry out all of these tasks. And of course, most importantly, like there are different NLP tools might be more suited to languages that are not English. So that's something that I will leave for a future workshop. And at this point, if I'm just if you have any questions for me or anything that you'd like to see covered as part of an NLP workshop, you can let me know, or you can add it to the chat. Either is fine. If there are any questions about SpaCy specifically, I'm happy to try and answer them. If you have questions about language models also. Let me look at this. Okay, so in our next workshop, we will be looking at regular expressions and what and how NLP and regular expressions work together to make searches more interesting. It is a relatively beginner-friendly look at not just regex, but also at other aspects of regular expressions like semantic regex. I'll also cover different ways in which regular expressions can be utilized. So how to run it on Python, how to run it on the internet, how to validate a regular expression, and so on and so forth. And I hope that all of you will be able to join me next week. And I hope that this workshop gave you a simple an overview of the terminology that NLP uses and what goes on inside the processing pipeline that a chat GPT or any language model uses in order to better understand human language. Okay. Thank you.
Meg, I have a question.
Yes, please.
At any time during this series of webinar seminars, are you going to discuss like maybe how to set up your own custom corpus for further NLP analysis?
I do have a workshop on text pre-processing for NLP. It may not be exactly what you're looking for, but we will look at different pre-processing steps that we will need in order to make a corpus machine readable. I'm not sure if that would be sufficiently overlapping with what you need.
Actually, I was saying more like the data management of the corpus. You know, the best way to store it, especially if it gets really large and contains some other JSON objects and or JSON type code.
I will maybe double check with some of my collaborators and see if it's being covered in any of the other workshops. But yeah, it's definitely it might not be within the scope of the NLP workshop, but I'll keep that in mind for future.
Thank you. Enjoyed it.
Thank you. Hey, Mithun, are you able to stop the recording?
Yeah, I'll just do that.
It's not letting me.